Hello and good afternoon friends, welcome to the CEC EduSet live lecture. Dear friends, as you know that we are carrying a series on chemical reactivity and mechanism, and so far we have conducted numerous sessions and we try to understand about various reactions. Dear friends, in our previous session we talked on reactions of alcohols. We tried to understand about the various reactions of alcohols. Dear friends, as we always have numerous data for you, numerous reactions for you, and sometimes it becomes inconvenient to wrap up the entire reactions in one particular lecture. So dear friends, today also we would be talking more on reactions of alcohols, or I would say we would be talking on the other reactions, the rest of the reactions which we were unable to discuss in a previous session, that is on alcohols. So for this we have again with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Dal Singh College, University of Delhi. And dear friends, the way she used to deliver her lectures with the number of examples in form of reactions, I hope that it becomes convenient for you to get in-depth knowledge if you are a student of chemistry, and this subject appears to be very interesting to you because of all her efforts. So I would like to welcome our guest Dr. Vandana. Dr. Vandana, welcome to the EduSet lecture.
Thank you so much. Thank you so much, ma'am. Hello viewers. In the series of chemical reactivity and mechanism, we were discussing about the reactions of alcohols. So the reactions so far we have done in the last two lectures are physical properties of alcohols, reactions with phosphorus trihalides, reactions with phosphorus pentahalides, elimination reaction, catalytic dehydrogenation of alcohols, haloform reactions, chemical test for alcohols, Lucas test, chromic acid oxidation test, Victor-Meyer's test, and about ethanol, their preparations and reactions. Today I will discuss about the oxidation reactions of alcohol, about methanol, its preparations and reactions. In the next I will discuss about the ethane 1,2-diol or ethylene glycol, its preparations and reactions. Oxidation reactions of alcohols. Oxidation of primary alcohol give aldehyde and then carboxylic acid. You can see in the slide that primary alcohol will give first of all aldehyde, and further oxidation will give you carboxylic acid. If we oxidize secondary alcohol, we gives ketones, and tertiary alcohol could not oxidize until unless we break the carbon-carbon bond. So we can simply say tertiary alcohol cannot be oxidized. Now what the question arises in our mind, what is oxidation? Simply oxidation involves either removal of 2 hydrogen or addition of 1 oxygen. In oxidation, removal of electrons takes place. If we use basic reagent, only proton from the hydroxyl group can be removed. But to oxidize primary alcohol to aldehyde, we need to remove carbon hydrogen proton with a pair of electrons, that is we can say hydride ion H minus. For this we require oxidizing agent. So you can see in the reaction it shows the primary alcohol base can abstract only a proton, but if we taking oxidizing agent then it can convert primary alcohol to aldehyde. For example, hexanol is oxidized by PCC. We will discuss in later what is PCC in dichloromethane to hexanol. Carviol, it is an impure natural product and can oxidize to pure carbon by PCC supported on alumina in hexane solution. In both cases, pure aldehyde or ketone was isolated by distillation. These are the reactions in which you can see hexanol can convert it to hexanol and carviol can convert it to carvion. First of all, we are discuss with oxidation of alcohols with potassium dichromate and sulfuric acid. Primary alcohols are oxidized to aldehydes on warming with potassium dichromate and aqueous sulfuric acid. Aldehydes are further oxidized to corresponding carboxylic acid as we said earlier. These are the examples. You can see ethyl alcohol when reacts with potassium dichromate in sulfuric acid, it will gives you acetaldehyde, and this acetaldehyde further oxidized to give acetic acid. Secondary alcohols are oxidized to ketones. Ketones are not further oxidized under the reactions conditions. Another example is here isopropyl, that is secondary alcohols which is converted to acetone with the help of potassium dichromate and sulfuric acid. This slide shows the mechanism. First of all, formation of HCrO4 negative takes place, that is chromium 6 from dichromate ion. In acid, chromium 6 with the alcohol form chromate esters, and chromate esters decompose by elimination of chromium 4 species, which subsequently react with chromium 4 to yield chromium 3rd. Chromium 6 oxidation state is orange in color and chromium 3rd oxidation state is green in color. So, you can easily identify whether the alcohol is oxidized or not with the conversion of the color from orange to green. You can see the mechanism also. First of all, dichromate can changes to HCrO4 minus, then it reacts with an alcohol to give a chromate ester. After that, there is a removal of electrons and chromium 6 converted to chromium 4, which further oxidize to give chromium 3rd. Tertiary alcohols are first dehydrated to the corresponding alkenes. The alkenes subsequently undergo oxidative cleavage at the double bond to yield a mixture of ketone and carboxylic acid, each containing fewer carbon number than the original alcohol. For example, you can see 2-methylbutane 2-ol. When reacting with H2SO4, first of all it gives 2-methylbut-2-ene, which on reaction with potassium dichromate and sulfuric acid will give you acetic acid as well as acetone. Next, oxidation with chromium compounds. Orange chromium 6 compounds are good oxidizing agents. They remove hydrogen from organic compounds and are themselves reduced to green chromium, that is chromium 3rd. Among various chromium compounds, polymeric oxide CrO3 is important. It is an anhydride of chromic acid. Water breaks up a polymer to give a solution of chromic acid. You can see here, this is CrO3, chromium 6 oxide, which can give chromic acid with the help of water. Chromic acid is best avoided if acid sensitive alcohols are to be oxidized, and alternatives can be used, which are PCC, PDC, etc., which I will discuss later on in this lecture itself. Chromium 6 can remove electrons to form chromium 3rd by a cyclic mechanism on a chromium 6 ester. First of all, one hydrogen is removed from OH to make the ester and the second is removed in this cyclic mechanism. You can see that primary alcohol when reacts with CrO3, there is a formation of chromate ester, and then there is a removal of proton and chromium gets 2 electron and changes to chromium 4. It is an unstable oxidation state which further oxidizes to chromium 3rd, which is green in color. Alcohols containing a double or triple bond can be oxidized to corresponding unsaturated carbonyl compound by Jones reagent in acetone medium at 0 to 20 degrees Celsius. What is Jones reagent? It is aqueous chromic acid in dilute H2SO4. These are the examples. You can see how the alcohol can convert it to carbonyl group or to ketonic group or aldehydic group. So, now question arises, why PCC and PDC are good oxidizing agent for alcohols than Jones reagent? Because Jones reagent first converts alcohol to hydrate. You can see in the reaction that alcohol will convert first to hydrate, then oxidize to acid. So, to avoid water, PCC and PDC are good alternatives. Now, what are PCC, PDC and other possibilities for oxidation of alcohols? PCC is, you can see, it is pyridinium chlorochromate. You can see the structure of PCC. It is C5H5NH plus Cl CrO3 minus, which is called Corrèze reagent, obtained by adding pyridine to a solution of chromium trioxide in HCl. PCC oxidizes primary alcohols to aldehydes in good yields and does not oxidize aldehydes further. Secondary alcohols are oxidized to ketones. These oxidations are carried out in anhydrous methylene chloride. Carbon-carbon double bond and triple bond remains unaffected towards oxidation under these conditions. So, these are the examples you can see. First of all, there is a preparation of PCC, how we can prepare PCC, that is Corres reagent. Then there are two examples in which PCC is used along with methylene chloride at 25 degrees Celsius to convert the alcohol to the aldehyde group. Another useful oxidizing agent also developed by Corre, which is pyridinium dichromate, that is short form PDC. You can see the structure, pyridinium dichromate, molecular formula C5H5NH plus, pyridinium chromate, dichromate Cr2CO7 whole twice 2 minus. It is prepared by chromium trioxide, pyridinium and water. PDC oxidizes primary alcohols to aldehydes without further oxidation. It also oxidizes allylic alcohol to alpha beta unsaturated carbonyl compounds. Chromium trioxide pyridine complex, that is CrO3 2C5H5N, called Collins reagent, is also used. This is the structure of pyridine trioxide chromium complex, which is called Collins reagent. These are the examples in which PDC is used in the solvent dimethylene chloride and DMF dimethyl fluoride. The first reaction carried at 25 degrees Celsius to convert the alcohol to the ketone, and in the second reaction DMF at 0 degrees Celsius is used along with PDC, pyridinium dichromate. Another useful mild oxidizing agent is manganese dioxide. It is specific for oxidizing allylic and benzylic alcohols to corresponding carbonyl compounds. For example, you can see allyl alcohol can convert it to acraldehyde, that is CH2CHCHO, or acrolein when reacts with manganese dioxide at 25 degrees Celsius. Another example is here, benzyl alcohol when reacts with manganese dioxide at 25 degrees Celsius, it will convert it to benzaldehyde. A primary alcohol can be converted into corresponding aldehyde by converting it first into a tosylate ester, which we have discussed in previous lecture also, or an alkyl halide, then oxidizing the tosylate or halide by dimethyl sulfoxide, that is CH3 whole twice SO, DMSO, dimethyl sulfoxide, in presence of sodium bicarbonate. These are the examples. For example, octane 1-ol first of all converted to tosylate with the help of tosyl chloride and pyridine. The product is 1-octyl tosylate. This is then reacts with DMSO and sodium bicarbonate and converted to octanol. Another example is here with benzyl chloride. First of all reacts with tribromide phosphorus, which is converted to benzyl bromide. Then with the help of DMSO and sodium bicarbonate, it will convert it to benzaldehyde, again a aldehyde. For synthesis of very sensitive aldehydes, we need very mild oxidizing agent. One of these mild oxidizing agent is TPAP. What is that? It is tetra N propyl ammonium perruthenate, which is pronounced as TPAP. TPAP can used catalytically, avoiding the large amounts toxic heavy metals by products generated by most chromium oxidations, and you can see the example is here and yield is 97%. Next is the catalytic dehydrogenation of alcohols. When a primary alcohol in its vapor phase is passed over copper heated at 300 degrees Celsius, it undergoes dehydrogenation to give an aldehyde. For example, ethyl alcohol will give you acetaldehyde at 300 degrees Celsius with copper. A secondary alcohol on similar treatment undergoes dehydrogenation to yield a ketone. For example, isopropyl alcohol gives acetone. Here is the example. A tertiary alcohol, however, does not undergo same reaction but undergoes dehydration under similar conditions to give an alkene. A tertiary alcohol does not possess a alpha hydrogen, so it loses hydroxyl group and a beta hydrogen to form a carbon-carbon double bond. For example, you can see in the reaction tertiary butyl alcohol yields isobutylene. So, that is all about the oxidation reactions of alcohol. Now, we look about the methanol, its preparations and its reactions in detail. What is methanol? CH3OH occurs in nature as its esters. For example, as methyl salicylate in the oil of wintergreen and as methyl benzoate in dove oil. It is sometimes called wood spirit, wood alcohol or wood naphtha because in the past it was obtained by destructive distillation of wood. Now, preparations of methanol. First of all, it can be prepared by hydrolysis of methyl halides with aqueous sodium hydroxide or moist silver oxide. You can see methyl iodide when reacts with sodium hydroxide, it will give you the methanol. By the hydrolysis of methyl esters with aqueous sodium hydroxide, you can see methyl acetate when reacts with sodium hydroxide, it will give you sodium acetate along with methanol. Next preparation is by the reduction of formaldehyde with lithium aluminium hydride or hydrogen in presence of nickel catalyst. You can see the reaction which shows the formation of methanol when formaldehyde reacts with lithium aluminium hydride, it will give you addition product which on hydrolysis will give you methanol. Next preparation is industrial preparation, that is from water gas. Water gas is a mixture of carbon monoxide and hydrogen and it is obtained by passing steam over red hot coke. Here is the reaction. Next is the methanol is manufactured by passing a mixture of water gas and half its volume of hydrogen under 300 atmospheres over a mixture of zinc oxide and chromium trioxide that is used as catalyst at 300 degrees Celsius to give the methanol. Next preparation is a mixture of methane obtained from natural gas and oxygen is taken by volume 9:1 compressed to 110 atmospheres is passed over copper catalyst at 250 degrees Celsius. Methane is oxidized to methanol. Now, physical properties of methanol. It is a colorless inflammable liquid, boiling point 64.5 degrees Celsius. It is highly poisonous in nature. Drinking of methanol causes blindness and even death. It is highly soluble in water and miscible with ethanol and acetone. It combines with the anhydrous calcium chloride to form a crystalline compound. You can see the structure which is called alcoholate. Hence, anhydrous calcium chloride is not used for drying methanol. Reactions of methanol. Methanol shows almost all the reactions of monohydric alcohols except for dehydration to alkene. Here are some reactions. You can see first of all methanol reacts with sodium, a metal, to give the sodium methoxide. Then methanol when reacts with ethyl magnesium bromide, it will gives you the addition product. Then when it reacts with acetic acid, it will give you ester, that is methyl acetate. More reactions, when methanol reacts with acetyl chloride, again methyl acetate are the product when reacts with acetic anhydride also. Then methanol when reacts with HCl in presence of zinc chloride, it will give you chloromethyl. When reacts with PCl5 phosphorus pentachloride, again same product along with POCl3. When reacts with tribromophosphorus, bromomethyl is there as a product. When reacts with phosphorus along with iodine, iodomethyl product is there. When reacts with thionyl chloride, again chloromethyl compound is there. More reaction, methanol when reacts with H2SO4 dehydrogenation takes place, will give you sulfate product. Then further at 160 degrees Celsius it will give you dimethyl sulfate. At 100 degrees Celsius it will give you methyl hydrogen sulfate, which on 140 degrees Celsius with alcohol will give you dimethyl ether. With aluminum oxide or alumina, it will give you ether CH3O CH3, dimethyl ether. With copper at 300 degrees Celsius, it reduced to formaldehyde. With potassium dichromate, first of all it converted to formaldehyde, and further oxidation it will give you formic acid, which on further oxidation will give you carbon dioxide and water molecule. Now uses of methanol. Methanol is used as a solvent and an antifreeze. It is also used to denature ethanol and for preparing methyl esters and formaldehyde. Now the next compound is polyhydric alcohols. In this series I have taken ethane 1,2-diol or also known as ethylene glycol. Ethane 1,2-diol, you can see the structure, the 2-hydroxyl group attached to the adjacent carbon, so it is called dihydric alcohol. Its common name is ethylene glycol. Now the preparations of ethane 1,2-diol or ethylene glycol. First of all, we will discuss about the hydroxylation of ethylene. In this preparation, ethylene reacts with dilute alkaline potassium permanganate solution in the cold to give ethane 1,2-diol, that is ethylene glycol. You can see the reaction. Ethylene when reacts with potassium permanganate with water, it will give you ethylene glycol along with manganese dioxide and potassium hydroxide. Next preparation is hydroxylation of ethylene to ethylene glycol can also be accomplished by the reaction of ethylene with osmium tetraoxide, that is OSO4, and subsequent decomposition of the product cyclic osmate ester with aqueous sodium sulphide solution. Reaction is there. Ethylene when reacts with osmium tetraoxide, you can see osmium at the center and 4 oxygen with double bond. First of all will give you cyclic ester, that is cyclic osmate ester. When it reacts with sodium sulphide, it will give you ethylene glycol. Hydrolysis of ethylene dibromide. Next preparation for ethylene glycol. Ethylene dibromide on heating with aqueous sodium carbonate solution yields ethylene glycol. You can see the reaction in which ethylene dibromide when reacts with sodium carbonate will give you ethylene glycol along with sodium bromide and carbon dioxide. A better yield may be obtained by first converting ethylene dibromide to ethylene glycol diacetate by reaction with potassium acetate and then hydrolyzing the diacetate with aqueous sodium hydroxide. Here is the reaction. Ethylene dibromide when reacts with potassium acetate along with acetic acid and heat, it will first of all give you ethylene glycol diacetate, that is ester. When it reacts with sodium hydroxide, it will give you ethylene glycol along with sodium acetate. Next preparation is the hydrolysis of ethylene chlorohydrin. Ethylene is allowed to react with hypochlorous acid, which is HOCl acid, to form ethylene chlorohydrin. You can see in the reaction, first of all ethylene reacts with hypochlorous acid to give ethylene chlorohydrin, that is ClCH2CH2OH, which is then boiled with aqueous sodium hydrogen carbonate, that is NaHCO3, along with heat to give ethylene glycol, that is CH2CH2OH. Next is the hydrolysis of ethylene oxide. Ethylene glycol is manufactured by the hydrolysis of ethylene oxide with steam at 200 degree under pressure or with dilute HCl or H2SO4 at 60 degrees Celsius. Ethylene oxide is prepared industrially by passing a mixture of ethylene and air under pressure over silver catalyst at 250 degrees Celsius. You can see in the reaction that there is ethylene, and when it reacts with passed oxygen along with silver at 250 degrees Celsius, first of all it give you ethylene oxide. Then hydrolysis of this ethylene oxide will give you ethylene glycol at 60 degrees Celsius. Physical properties of ethane 1,2-diol. It is a colorless viscous liquid, boiling point 197 degrees Celsius. It has a sweet taste, its boiling point is high. When we are talking about the boiling points of any compound, boiling point simply depends upon the extent of hydrogen bonding. If a compounds have high extent of hydrogen bonding, then its boiling point will be high. If extent of hydrogen bonding is low, then boiling point of a compound will be low. So, we can say on the basis of hydrogen bonding, we can define or we can assume the boiling point of the compounds. Especially in ethane 1,2-diol, due to intermolecular hydrogen bonding, the boiling point is high because it forms intramolecular hydrogen bond in the Gauche conformation, but not in its anti-conformation. This imparts greater stability to Gauche conformation than the anti-conformation. So, to understand clearly the hydrogen bonding extent for boiling point, we need to understand the Gauche conformation and anti-conformation of ethane 1,2-diol. And you can see in the structures what is Gauche conformation and what is anti-conformation. You can see that in Gauche conformation, the hydroxyl group are on the same side. That is why it is called Gauche conformation. And what is the hydrogen bonding? When hydrogen of an hydroxyl group or any electronegative atom, oxygen, nitrogen, sulfur with hydrogen, this hydrogen when have interaction with electronegative atom of another group like OH, like NH, like SH, it is intramolecular because hydrogen bonding takes place within the molecule. But when we are talking about anti-conformation, it is not possible. You can see the structure. In anti-conformation of ethane 1,2-diol, the OH groups are opposite in direction, or we can say there is no possibility of intermolecular hydrogen bonding. So, we can say greater stability to Gauche conformation than to anti-conformation. Ethylene glycol exists almost exclusively in its Gauche conformation because of its stability. Ethylene glycol is miscible with water and ethanol in all proportions but insoluble in ether. That is, we can say it is miscible with water and insoluble in organic solvents. For example, here we are talking about the ether. And whenever we are talking about the hydrogen bonding or boiling point, we can also subsequently must talk about the solubility. Higher the hydrogen bonding possible with water in for any compound, higher will be the solubility. So, when we are saying there is a high extent of hydrogen bonding with ethane 1,2-diol, we can say the solubility will also be high. Now, the reactions of ethane 1,2-diol. There are two primary alcoholic groups present in ethylene glycol which behaves in a similar manner as the primary alcoholic group of monohydric alcohols. Usually, one of the primary alcoholic group reacts first and the second one does not react until the reaction of first one is complete. So, the reactions of second hydroxyl group sometimes require more vigorous conditions. First of all, we are discuss about the reaction with sodium. You can see in the slide that ethylene glycol, when reacts with sodium at 50 degrees Celsius, it forms a salt. It is sodium salt, monosodium salt, and it reacts with another mole of sodium at higher temperature, that is 160 degrees Celsius, to form a disodium salt. You can see the reaction, the structure of monosodium. So, first of all, one hydroxyl group reacts with sodium, form a salt, then the secondary or second hydroxyl group will react, but you can see the temperature is higher. That is why we said in the last slide that sometimes it is difficult to complete the reaction with both the hydroxyl group. Next reaction is reaction with hydrogen halides. Ethylene glycol reacts with hydrogen chloride and 160 degrees Celsius to form ethylene chlorohydrin. You can see in the reaction, first of all it reacts with HCl at 160 degrees Celsius and will one hydroxyl group converted to chloride group and will give you ethylene chlorohydrin. And then later reacts further with hydrogen chloride at 200 degrees Celsius. Again, you can notice the temperature is high for the second hydroxyl group and which gives you ethylene dichloride at 200 degrees Celsius. And similar reactions takes place with hydrogen bromide. Next reaction is with reaction with phosphorus halide. Here we are taking two, phosphorus pentachloride, phosphorus tribromide. Ethylene glycol reacts with phosphorus halide to form corresponding ethylene dihalides. Ethylene diiodide, however, loses a molecule of iodine under the reaction condition to form the ethylene. So, you can see along with PCl5 or phosphorus pentachloride, it will give you dihalides with POCl3, and with phosphorus tribromide, it will give you dibromide along with H3PO3, phosphoric acid. With the Pi3, the products are different. First of all, we get the ethylene diiodide and then it will gives you ethylene by elimination of iodine molecule. Reaction with thionyl chloride yields ethylene dichloride. You can see ethane 1,2-diol when reacts with thionyl chloride, this is SOCl2, it will give you dichloroethylene with sulfur dioxide and HCl. Next reaction is with nitric acid. Ethylene glycol reacts with concentrated nitric acid in the presence of concentrated sulfuric acid to form ethylene dinitrate. You can see the reaction ethylene glycol when reacts with oxidizing agent, strong oxidizing agent, that is concentrated nitric acid along with sulfuric acid, it will give you ethylene dinitrate. Next reaction with triiodophosphorus, it will give you first of all ethylene diiodide and then with ethylene. Reaction with thionyl chloride yields ethylene dichloride. Next reaction is with carboxylic acid. Reaction of ethylene glycol or ethane 1,2-diol with carboxylic acid yields mono and diester depending on the relative amounts of ethylene glycol. Here you can see ethylene oxalate is formed when ethylene glycol reacts with oxalic acid. So, it will gives a cyclic product. Other dicarboxylic acids react with ethylene glycol to form polymers, or you can say polyesters. How it will gives the polyester, you can see in the next reaction. Terephthalic acid, what is that? It is benzene 1,4-dicarboxylic acid which undergoes condensation polymerization. Condensation means when we are talking about the term condensation, addition will take place but with the elimination of small molecules, you can say water molecule, you can say carbon dioxide. So, condensation includes the addition of the reactant with the elimination of small molecule. Condensation polymerization with ethylene glycol to form a polyester which is known as terylene or Dacron. What is that? It is a synthetic fiber because we are synthesizing in lab. It is not naturally occurring or we are not taking it from nature, that is why it is called synthetic fiber. You can see the structure of terephthalic acid. A benzene molecule at the center, 2 carboxylic group are on the terminals with N number. When it reacts with ethylene glycol, condensation will take place. You can see in the reaction that water molecules is also there as a side product, and you can see the structure of polymer which is terylene is there. Now the next reactions with aldehydes and ketones. Ethylene glycol reacts with aldehydes and ketones in the presence of para-toluene sulfonic acid to form 5-membered cyclic acetals and ketals respectively. These are called 1,3-dioxolanes. How the reaction takes place? You can see in the reaction. Acetaldehyde when reacts with ethylene glycol in presence of para-toluene sulfonic acid, you can see para-toluene CH3, C6H5 is the toluene and sulfonic acid is this SO3H. It will gives you a cyclic 5-membered. You can count 1 carbon, 2 oxygen, 2 more carbon from ethylene. So, it is 2-methyl 1,3-dioxolane, or we can say acetaldehyde ethylene acetal. Next reaction is with butane 2-on. When it reacts with ethylene glycol, then you will get the product. You can see again a cyclic product is there, pentacyclic, 5-membered, 2-ethyl 2-methyl 1,3-dioxolane. Another reaction is there, cyclohexanone, a ketone, a cyclic ketone. When reacts with ethane 1,2-diol, it will gives you 1,4-dioxo-spiro-4,5-decane, or we can say cyclohexanone ethylene ketal. The formation of 1,3-dioxolane is useful because it serves as a protecting group for aldehydes and ketones, because if we are doing for a reaction we need to protect a group, then we can take the use of this reaction. It is stable in alkaline medium, but the ring opens up in dilute solutions. So, if a compound possesses both ketone and ester functional group and one desire to carry out transformation at the ester functional group with the reagent that that reacts also with ketone. One has to protect the ketone group first by ketal formation, as we have discussed in the last slide. Once the transformation at the ester function has been accomplished, the ketone function is regenerated by treatment with dilute acid. For example, you can see here how the ketonic group is protected by formation of dioxane with the help of ethane 1,2-dione. Then there is a reaction with Grignard reagent, methyl magnesium iodide, subsequently by ammonium chloride and water. So you can see COOCH3 methyl acetate group is converted to tertiary alcohol. So in the intermediate or in the middle, you can see, first of all we need to protect the keto group with the help of ethane 1,2-diol. Subsequently the further reaction on the ester group. You can see, first of all there is a addition product by Grignard reagent, that is methyl magnesium iodide, and followed by hydrolysis we get the tertiary alcohol. And this dioxane can also converted by dilute acid to keto group. If the ketone is not protected, the reaction yields a different product from that derived above. You can see what will be the different product if we are not protecting ketonic group before proceeding the another reaction. Now reactions with periodic acid, oxidative cleavage of glycol. When ethylene glycol is treated with periodic acid, that is HiO4, it undergoes oxidative cleavage at the carbon-carbon bond to form two molecules of formaldehyde, that is HCHO, the first aldehyde. Oxidative cleavage of glycols with periodic acid is called the Malaprade reaction. Sodium periodate, that is sodium NaIO4, may be used in the place of periodic acid. Here is the reaction. First of all, you can see the ethylene glycol, then periodic acid IO3OH. There is a formation of cyclic intermediate with the elimination of water molecules. Here 5-membered cyclic intermediate is there. Then there is a elimination, or you can say subsequent rearrangement. The first arrow shows there is a breakage of IO bond, another breakage of IO bond, and there is a formation of two molecules of formaldehyde along with iodic acid, that is HiO3. Next reaction is with lead tetraacetate, oxidative cleavage of glycol. What is lead tetraacetate? As you can see, the name indicates lead Pb tetraacetate, 4 molecules of acetate CH3COO. Lead tetraacetate also brings about oxidative cleavage of carbon-carbon bond of ethylene glycol. As a result, 2 molecules of formaldehydes are formed. In the reaction you can see the ethylene glycol when reacts with lead tetraacetate, that is CH3CO ka whole 4 Pb, it will gives you formaldehyde 2 molecules, lead diacetate, that is CH3COO ka whole twice Pb, and 2 molecules of acetic acid, that is 2CH3COOH. How the reaction proceed? It is given by Craigie, a scientist. The reaction is believed to proceed through a cyclic intermediate. You can see the ethane 1,2-diol or ethylene glycol when reacts with tetraacetate lead, there is an elimination of 2 molecules of acetic acid, and you can see a 5-membered cyclic intermediate. Then there is a rearrangement or breakage of bond and formation of new bond which will give you 2 molecules of formaldehyde along with the elimination of lead acetate. However, the reaction may also proceed through an acyclic path as shown below. You can see the ethylene glycol. What is the difference between this structure with the previous structure? You can see the OH group are on the same side, and here the OH group on the opposite side, that is anti-conformation. And the intermediate which forms, you can see how it forms in the structure, and then there is a bond formation or breakage to gives formaldehyde along with lead acetate and acetic acid. So, there are 2 possible mechanisms for this reaction. One is the given by Craigie through cyclic intermediate, another one is acyclic path through acyclic path, because there is no formation of cyclic intermediate. Next reaction is with oxidation with nitric acid. When ethylene glycol is oxidized with nitric acid, glycolic acid and oxalic acid are formed, which may be readily isolated. Other oxidation products, namely glycoaldehyde, glyoxal and glyoxalic acid, have also been isolated in poor yield, because these are more readily oxidizable. Oxalic acid is further oxidized to carbon dioxide and water. You can see the various products, oxidized product of ethylene glycol. First of all, you can see the glycoaldehyde. It is taken from glycol with 1 molecule of aldehyde, then glycolic acid, double L acid, then glyoxal CHO, glyoxalic acid, because 1 molecule is oxalic acid, COH, CHO, oxalic acid. So, these are the various products which can be isolated by the oxidation of ethylene glycol. Next reaction is with dehydration. What is dehydration? You are very much aware of the fact, the removal of water molecule from reactant. Ethylene glycol may undergo either intramolecular or intermolecular dehydration depending on the nature of dehydrating agent and other reaction conditions. What are the dehydrating agent used in our normal lab, which is in colleges, is H2SO4. Ethylene glycol, when heated at 500 degrees Celsius, undergoes intramolecular dehydration, that is removal of water molecule within the same molecule. It is also called cyclodehydration to give ethylene oxide, because the product you are getting here is cyclic product, or you can see it is ethylene oxide or epoxyethane or oxirane. We have discussed these names when we were discussing about the epoxide. When ethylene glycol is heated with anhydrous zinc chloride, it undergoes intramolecular dehydration to form acetaldehyde. Again, we are taking here anti-form of ethylene glycol. You can see what happens here when reacts with zinc chloride. It will gives you addition product, right, because oxygen is electronegative atom, so it will attach to oxygen. So, positive charge will acquire by oxygen. Now, it becomes electrophilic in nature. So, what happens here when it becomes electrophilic in nature? It will pull the covalent bonded electron towards itself, right, and this hydroxyl group then approaches to CH2 group, which loses the electron, which loses the electrons, and will form a epoxide ring. You can see the epoxide ring. Then what happens? Along with the formation of epoxide ring, there is a removal of this product HOZnCl2. Now it abstracts the proton from the epoxide ring because it is become more acidic in nature as it attached to the oxygen. Then there is a removal of zinc chloride and water molecule to form the ethylene oxide. Now it again reacts with zinc chloride and will give you addition product because oxygen is electronegative in nature. It will attach to the zinc metal and hence acquire the positive charge. So it becomes the electrophilic in nature again. When it becomes electrophilic in nature, it will pull its covalently bonded electron towards itself. So you can see there is a ring opening takes place over here and followed by 1,2 hydride shift. You can see what is 1,2 hydride shift. There is a shifting of hydride ion from one carbon to the another carbon, that is why it is called 1,2 hydride shift. And subsequent elimination of zinc chloride will give you acetaldehyde because you can see in the second last product oxygen having positive charge. As it is becomes electrophilic in nature, again it will pull the covalently bonded electron towards itself. So pushed up the zinc chloride for elimination. So you can see by this mechanism we are getting here from ethylene glycol with zinc chloride to acetaldehyde. When ethylene glycol is heated with phosphoric acid, it undergoes intermolecular dehydration to give diethylene glycol. Diethylene glycol is used as a solvent. You can see when two molecules of ethylene glycol reacts with phosphoric acid, it will give you diethylene glycol. When ethylene glycol is distilled with fuming sulfuric acid, it undergoes bimolecular cyclodehydration to form 1,4-dioxane. What is the use of 1,4-dioxane? It will used as a good solvent because for number of preparation we need good solvent which are inert in nature and does not affect our main reaction. You can see the reaction how it follows. First of all, there is a dehydration takes place with the help of dehydrating reagent, that is H2SO4, and formation of diethylene glycol. Again further dehydration will form a cyclic compound, that is dioxane. Now uses of ethane 1,2-diol. It is used as a solvent, as an antifreeze in motor car radiators, for manufacture of terylene, diethylene glycol, 1,4-dioxane and glycol stearate which is used as lubricant, as a de-icing fluid for aeroplane wings and as a preservatives. So these are the uses of ethane 1,2-diol or glycol. So what is the summary of today's lecture? We have discussed about the various oxidation reaction in which we have discussed what is the oxidation reaction actually, and then oxidation of alcohols with chromium compounds, with potassium dichromate compounds, with manganese dioxide, with catalytic reduction and many more like TPAP. Then we have discussed today about the methanol, the preparations of methanol, how can we synthesize methanol in lab and industrially, reactions of methanol, it is a primary alcohol, so it will give all the possible reactions of primary alcohols. Then we have discussed very important alcohol ethane 1,2-diol which is also known as ethylene glycol. So we have discussed the preparations of ethane 1,2-diol and reactions of ethylene glycol. So for that, thank you so much for patiently listening me.
With this note, thank you ma'am, thank you so very much for giving us a productive session once again, and I hope that all the students who might have watched this lecture would be benefited from it. And dear friends, this lecture was especially for you, and here we discussed about the various reactions of alcohols. Now I want to ask you ma'am, what else are we going to cover in the next sessions?
In the next session, I would like to take the, because we have discussed about what are the alcohols, what are the classification of alcohols, their important reactions, their important mechanisms for reactions. Now, I will take the, in this series chemical reactivity and mechanism, another functional group or another compound, very important compound you can see all around among you all, carbohydrates. So, I will discuss in next lectures what are the carbohydrates and how they are important in our life.
Definitely, this means that this is a very huge series on chemical reactivity and mechanism, and we would be going to learn more and more under this series. And for this, I believe that, and I strongly feel that we should keep calling you, we should keep inviting you, and we want Dr. Vandana to give her most of the times to the lectures,
so
that
thank you so much.
it becomes convenient for the students to get the knowledge as much as they can, as the students are preparing for their examinations also, which are coming very soon. So dear friends, if you have liked this lecture, if you want to give your feedback, or if you want to ask any question from Dr. Vandana, then you can mail us at info.cc@nic.in. We would be waiting for your suggestions also and your questions also the next time when Dr. Vandana visits our studio. That is very soon. Then we would love to solve your queries, as well as if you want to see this lecture and if you feel that you want to access this lecture, you want to see this lecture number of times to prepare for your examinations, then you can see this lecture with the help of YouTube, as very soon we are going to upload this lecture on YouTube, so that it becomes easier for you to get maximum knowledge through this lecture. As well as if you want to see all the lectures concerning this series on chemical reactivity and mechanism, so all the lectures given by Dr. Vandana are also there on the YouTube, so that it becomes easier for you to see the entire series in a chronology. So we would be meeting again. Till then, take care. Goodbye. Thank you, ma'am. Thank you so very much.